All right, guys, welcome to the channel. I am Professor Wolf, and I always found it frustrating having science professors that had no business teaching science. So hopefully I can provide you guys maybe an easier way to go about some topics, okay? So what we're going to do today is talk about osmosis, okay? Movement of water, okay? All right. So before we get to osmosis, there's something really important that we need to talk about, okay? We need to talk about passive transport, okay? So here is passive transport, okay? There's passive and there's active transport. Osmosis is a type of passive transport, okay? That pretty much just means that it does not require ATP in order for the movement of H2O, okay? So, what we're going to talk about with passive transport, we need to understand first gradients and permeability, okay? So what I'm going to do here is I'm just going to draw a circle. And that circle can represent a cell, okay? It could represent anything. Let's just say it's a compartment, okay? Let's not even go that far. So we're going to have molecule X here. And we're going to have molecule X here inside, okay? So here, we'll say, we won't even give it a digit. We'll just say it's 40, okay? The concentration of molecule X inside here is 40, okay? See how I drew it bigger? Then molecule X outside the compartment is going to be 10. So, for a gradient to be present, here's a gradient, right? And a gradient moves from a higher concentration to a lower concentration. So, which way would molecule X move? In or out of this compartment? Okay, it's going to move out of the compartment, okay? All right? So that's a really important concept to understand, okay? So if I go over here and I draw X again here and here, and we're going to say it's 10 again, and we're going to say it's 10 inside the cell. Which way is X going to move? Okay, pause the video if you need to, okay? Okay, I'm going to pretend you paused, all right? So it's not going to move at all. No gradient equals no movement, okay? This is very important, okay? Now let's do one more example. I'm going to draw another compartment or cell, whatever you want to think about. And let's just say I'm going to do X here. We'll just keep it the same. Let's do 10. And we'll do X here. And I'll draw a little bigger. Let's say it's 40 again, okay? So which way it's going to move? Of course, it's going to move out, right? It's going down its concentration gradient, okay? It goes from a higher concentration to a lower concentration, okay? So then, let's just say we have molecule Z, okay? Let's just do Z, all right? And it is going to be 5. And inside, it's going to be, let's do something crazy. let's just say 80. Okay, so obviously, right, it's going to move out. Now notice that I drew this arrow here a lot bigger than I drew this arrow, okay? And that's because this gradient is bigger than this gradient, okay? So 80 minus 5 is 75, right? 40 minus 10, so this is going to be x, that's going to be z, right? That's molecule x, that's molecule z. That's going to be 30. That molecule z has the bigger gradient, okay? So with a bigger gradient, there will be more movement, okay? That's super important, okay? This is still going to move out of the cell, right? But this is going to have more movement out of the cell, okay? So now let's talk about permeability, okay? So permeability, and think permeability, think ability, okay? It's the ability of a molecule to move. Okay, that's what we're going to think about. Okay, so let's do this again. Now thinking about permeability in mind. Okay, we're going to have compound X to 40, and we're going to have X out here at 10, and we're going to do Z here at 80, and we're going to do Z out here at 5, okay? Now let's talk about the permeability, okay? Let's do a permeability of 1 for X, and let's say Z has no permeability, okay? 0, I'll make that Z permeability. That'll be X permeability, okay? All right, or let's just say it's 0.0001, okay? What's going to have more movement? Is it going to be molecule X or molecule Z? It's going to be molecule X, okay? So once you throw in permeability, that gradient, right? If they both equaled 1 permeability, compound Z would have more movement, okay? So that would have more influence on the cell, all right? So that's important, 2 important concepts, okay? Surface area is another one, but, we won't get into that. Pretty much the same concept. If you have higher surface area, you're going to have greater movement, okay? So why did I just show you guys that, right? Why did I show you the importance of those gradients? Well, that's going to help us understand osmosis, okay? So if we go here to osmosis, we're talking about the movement of water, okay? So there's a thing called osmotic pressure, okay? Osmotic pressure, okay? And this has to do with solute concentration, right? Sodium ions, solutes, right? So we're going to talk about how this influences the movement of water, okay? So we're going to draw our circle again, our compartment, okay? We'll just say this is a cell, all right? So this cell going to have these little dots in it. And those dots are going to be our solutes, okay? Those are going to represent our solutes, our sodium, our potassium, okay? And then out here in the interstitial fluid, we won't even get to that. We'll just call it a space. There's solutes out here as well, okay? Now, you can clearly see that there is a lot more solutes inside this cell than there is out here, okay? So there is going to be higher osmotic pressure here inside the cell, okay? So that solute concentration is what dictates osmotic pressure. And ultimately, that osmotic pressure is what is going to dictate the movement of the water, okay? And an important thing to remember about this osmotic pressure is that it is a pulling force, okay? It pulls water. So it is going to pull water into the cell, okay? And that's dictated by those little solutes, all right? Okay, so let's just say that we have an osmotic pressure in our cell that's real high, okay? We'll say a high osmotic pressure. And then we have low, right? So same situation, right? This is going to have a higher solute concentration, right? We already know that because it has a high osmotic pressure. Okay, so we know it has more solutes inside this cell. Well, we are going to call this hypertonic. Okay? And then in this compartment, just in this space here, okay, this has less solutes than what's inside that cell. So it would be hypotonic. And that is pretty much the basis of osmosis, okay? And if they were even, let's just say they were even, right? Even amount of solute concentration, even amount of osmotic pressure, okay? Would there be any movement of water? No, there wouldn't be, okay? There would be no movement of the water because the gradient is the same. There is no gradient. If you go back up here, no gradient, no movement, okay? So now, here, in this situation, the osmotic pressure is the same because the solute concentration is the same. So there is no movement of water because there is no gradient, okay? And this is called isotonic, okay? That's when this is all equal to each other, okay? The solute concentration is equal in both compartments in the interstitial space here and inside the cell here, okay? All right, I hope that was helpful, and I appreciate you guys, okay? Take it easy, take care of your mental health, okay?